Since water is a fundamental building block of stars and planets, exoplanet worlds must surely have it in abundance. But if you're looking for life, you need to find liquid water, and plenty of it. To find it, astronomers take their cue from a fairy tale.
Everybody knows the famous story of Goldilocks and the Three Bears and the cup of porridge, where one was too hot, one was too cold, and one was just right. When it comes to cooking up life like a porridge, you need to have an environment that's not too hot, not too cold, just right. And traditionally, we look for that at a certain distance around a star.
At first, astronomers based this magical distance, known as the Goldilocks zone, on the Earth's orbit around the Sun. But as they found more and more exoplanets, they've had to reevaluate the boundaries for liquid water.
There isn't a single distance. It depends on the brightness of your parent star. A dim star, you need to be closer. A hot star, very bright, you need to be farther away.
Scientists have calculated just how many rocky planets may lie within the Goldilocks zone of their stars. It comes out to over 30 billion potentially watery worlds. Even more remarkably, recent discoveries have shown us it's not just planets that can bask in the warmth of the Goldilocks zone. There may be moons painted blue with oceans too.
Most of the planets we're finding are big Jupiter-sized planets. However, a lot of them are orbiting roughly where the Earth is orbiting the Sun. So even if the planet that we're finding can't support life, it could have a moon with an atmosphere that could support life.
And the biggest of these rocky moons may resemble our home.
There could be billions upon billions of exomoons out there, and even perhaps countless paradises teeming with life.
David Kipping searches for exomoons by looking for double dips in the brightness of distant stars.
We look for exomoons in a very similar way to the way that we look for planets, by looking for them transit their host star. Now, if that planet had a moon, then we should expect to have one big dip due to the planet, and then one smaller dip either to the left or to the right due to the moon.
Habitable exomoons may play host to one of the most spectacular sights in the universe. Imagine a warm, rocky world, just like our own, with oceans and mountains. But in the sky, a massive ringed planet with a fiery sister moon shooting hot magma into space. Exoplanets, and now the vast potential of exomoons, hint at a galaxy filled with the possibilities for life. But a rocky surface and liquid oceans may not be enough. Biology needs the breath of life, air. Backlit by the sun, a halo appears around the Earth. A pale blue ring of light, our atmosphere, and we owe it everything. The Earth's atmosphere provides the gases that fuel the biochemistry of advanced life. But it also protects the oceans from the full fury of the sun's rays, preventing the water from boiling away into space. Without an atmosphere, there would be no wind, no rain, no fresh water, and probably no life.
Atmospheres are absolutely essential for life. Take a look at the planet Earth, and you realize that just like the skin of the apple preserves the apple, well, the atmosphere of our planet preserves the oceans and makes possible the presence of life as we know it.
Scientists in search of living exoplanets hope to detect the thin, gassy envelope that should surround these alien worlds. To do it, they're turning to the power of rainbows. In the same way that water splits sunlight into a rainbow, astronomers use instruments to split starlight into a band of colors called a spectrum. It's one of the oldest tricks in science, and one of the most revealing.
Several hundred years ago, scientists first began to take something like a prism and put it in front of their telescope. So they started taking the light from stars like the sun and actually spreading it out into a spectrum. And what they saw was kind of surprising. So instead of seeing a continuous rainbow of light, they saw that rainbow, but they saw these dark lines superimposed on top.
Each chemical element in the star's atmosphere absorbs different parts of the spectrum, creating signature dark bands.
For instance, up at the top, there's a pair of lines in the yellow part of the spectrum, which are due to sodium.
Like a DNA profile for stars, spectral analysis has taught us almost everything we know about stars today. But these same lines may hide a marvelous secret: the faint signal of alien atmospheres, and perhaps also alien life.
So the challenge is that these planets are very small and very faint. So we can't actually go and directly measure the light emitted from the planet the same way that we go and measure this lovely spectrum for the sun. Instead, we have to rely on more indirect methods. So one indirect way of doing that is to wait until the planet passes in front of the star.
When the light of a star passes through an exoatmosphere, the gases that surround the planet should stamp their own faint lines on the star's spectrum.
So as we watch the light from the star transmitted through that atmosphere, its atmosphere is going to act like a little filter. So part of the starlight's going to pass through that atmosphere, and we're going to see that imprinting extra lines on it, which are due to the planet's atmosphere. So that change in the spectrum tells us something about the properties of the planet's atmosphere.
The one chemical astronomers most want to find is oxygen, because only life can produce enough oxygen to be easily detected. It's a so-called biosignature. The race is now on to find biosignatures in the atmospheres of rocky exoplanets. And while some groups look for rainbows indirectly, others are tackling the challenge head-on.
27 to 29. All right, we're off.
Ben Oppenheimer is part of a team trying to take direct photographs of exoplanets using massive ground-based telescopes.
Awaiting instructions.
We're within minutes of taking our first long exposure, and I hope it's good.
The greatest challenge to imaging exoplanets is the blinding light of the parent star, which shines tens of millions of times brighter than the planet itself. The trick is to stop the light of the star from entering the telescope's sensors by blocking it, using a series of masks and lenses called a coronagraph.
Right now we're standing right underneath the telescope's primary mirror, and the light comes through a hole in the middle of the mirror and goes into this crazy box here, which is full of optics, motors, sensors, and electronics that all allow us to precisely control the starlight that's coming through the system.
Using state-of-the-art software, they manipulate the coronagraph to black out the unwanted light.
Under good conditions, we can actually carve dark holes into this image of the star so that we can see really faint things in those regions.
Coronagraphs present an intriguing problem, though. Errors within the optics produce tiny flares of starlight called speckles that look just like exoplanets. But Ben has come up with an ingenious way to tell speckles from planets.
So we've developed a technique where we exploit an aspect of speckles, which is that they change position in the image depending on what color you take your image at.
Image processing.
So Ben takes the same image of the star through different color filters and runs them like a movie. The speckles appear to move across the screen, but the planets stay stock still, allowing Ben to easily pick them out.
And so I'd like to point out that there is a little thing right here that if you watch, for you're careful, you'll notice that it doesn't move and the speckles are washing over it.
This stationary blob